Hello everyone, my name is Alex Worthington. I'm the Technical Director at Theater Squared, and today I want to talk to you a little bit about understanding deflection criteria. Everything I'm talking to you about today is from this book, Structural Design for the Stage. It's a fantastic resource, and so if you are a TD or if you're handling a lot of structural design based off of a designer's packet, or you're just kind of making it up as you go along, this is a fantastic resource to just kind of make sure that not only, going with your gut instinct is great, especially if you have a lot of experience, but if you're doing something new that you're unsure about and you just want to make sure it's safe for you and everybody around you and people performing on it, on that set, then this is a perfect resource. It's very easy to use, and the appendices in the back of the book are great, and that's actually what we're going to be using today. So, what is deflection? Well, deflection is, take a look at this graphic right here. Deflection is just kind of a metric we use to say what is an allowable amount of not bending but bowing. Will this beam that we've selected bow too far before it hits a failure mode that we are comfortable with? Should we be using a 2x4, a 2x6, or a 2x8? That's basically what we're talking about today. And so in this graphic, you'll see, we have a load at the center that with a P that would be a point load. We'll be examining the difference between that and then a uniformly distributed load, which would just be a load like the weight of the beam itself, or if we have something on top of our platforms the entire way, like some type of scenic treatment. That's what we're going to be examining today. Some important definitions, just so we all kind of communicate on the same page. A beam, that would be just kind of a side member of your platform. So if it's a 4x8, it would be that 2x4 standing straight up. A column is what we generally refer to as a leg in the theater industry in the United States. Loading condition, what I just talked about. This is the weight or load on your platform or your beam. And then types of loads: uniformly distributed load or uniform loading condition, as I have listed right here. I kind of go back and forth between saying uniform or evenly distributed load. Point being, those two things are the same. And then a point load, just a heavy weight that's in the middle or some arbitrary spot. Sorry, excuse me. Some arbitrary spot on your beam, like a hanging chandelier. So when we start this process of figuring out the deflection criteria and where we want to start with our entire project, we typically start with drawing a free body diagram of our loading condition, and we do a couple of checks. We make sure that the sum of our forces, our vertical forces, are equal to 0, because we want to make sure that we are in static equilibrium. If we're not in static equilibrium, that means that our structure is moving, and we super do not want that. We want everything we build to just, be where we want it to be and only move when we want it to move. So making sure that the sum of the vertical forces are equal to 0, let's imagine that this point F is in the middle of our free body diagram right here, and let's say F is 100 pounds. So if F is in the middle, we would automatically assume that capital A and capital B, which would be our legs, our reactions for our columns, would be equal to 50, because we would just divide that number perfectly in half. And so where that can kind of get us in trouble, because, we just moved F to the center. Well, that might be a really good test for us in deflection, as you'll see in a moment. But once we start calculating loads for our columns, we'll definitely want to make sure that we have that F in the correct spot, because B would probably be seeing a greater load than A. So here's a kind of drawn out free body diagram. Right here we see beam weight, which is 10 pounds per linear foot. That's a little w. Another little w of 200 pounds per linear foot. 14-foot long beam. So yeah, we have everything written out in feet. One thing I like to do before I dive too far in the math is just go ahead and just convert everything to inches, because at the end of the day, we're going to be looking for values in inches in the back of our handbook when we start selecting lumber. So let's kind of walk through this problem. And the reason why we're getting here is we're going to try and find big W, which is the combination of these two little w's right here. We're looking for our total load against this beam so we can test for deflection. So right here we see 1540. That's our total load. And when I test deflection quickly, I will just go ahead and move that 16.667 load to the center of the beam so I can just run a deflection test really quickly. That's what I just said. Jump the gun a little bit. Oh, feel free to pause. If I go over something too quickly, just scroll back, pause, and hop back in whenever you're ready. Don't get too scared about this math right here, because the point of today is us not having to worry about this. But my point with this slide is kind of what I just touched on, making sure that when we get into the column math, and that's not this video, but when we get into the column math, we want to make sure that, you know, we're looking at the appropriate load. Reaction 1 here, R1 on the left side of this diagram, is seeing a much different load than R2. But conservatively, if we want to test a beam quickly and make sure it's going to handle this load, just move that heavier bit of load to the center, because the center of the beam is the weakest point of the beam. And so if it passes deflection there, then we know we're safe to build. So let's create a problem together. Another term we should know is the modulus of elasticity, and that's just a numerical value that is assigned to each type of material, whether it be wood, aluminum, or steel. There's a figure associated with each material that represents that material's stiffness. And so as you can see right here, I have pine and poplar, which is another type of wood, steel, and aluminum. I'm going to show you some case formulas here in a little while, and that will kind of give you an idea. You can swap these moduli out whenever you want to test for different values and selecting different materials for the same problem. And then moment of inertia is a material and that material shape. So, 2x4 versus 4x4, that material and its shape tendency to deflect or move under a given force. So it's a big term to kind of wrap your mind around, but just imagine a piece of lumber and how much force does it take to get it to move or deflect. And it's represented in a value of inches to the fourth, which is a little confusing. We're not going to focus too much on that today, but just remember, moment of inertia is a very important value that we are going to be testing against. So diving in a little bit more to deflection. Deflection itself is not a failure mode, so we're not talking about crushing, crumpling, shearing, anything like that. This is not going to be a test that represents the destruction of lumber under a load, but more so, what is this lumber capable of doing safely under this load? So, kind of touched on this a minute ago. Let's just add another leg under it, and maybe that is the right choice for you and your show, but every show is different. And let's say you're working with an outside designer and they want a big bridge. Rather than let's throw another leg under there, we can run a simple deflection test and say, actually, we are capable of that. All we need to do is buy X, Y, and Z piece of lumber. Or no, we can't do that because this requires a fairly large piece of lumber that we can't afford. So So this is just a really good way. This is another tool in the toolbox for us to open up our conversations with our producers and designers, and then hopefully also kind of make our product even better than it was before. So an illustrated example we can kind of see here on the left, a pretty standard 2x4 constructed platform with 6 legs, 3 legs on each side. And so I am assuming that that's a 2x4 because we have 3 legs. And then the image on the right, we see it only has 2 legs on each side. And so, how do we get from point A to point B on this specific problem? Not to mention the image on the right, those platforms are pretty high up, so that would actually be a pretty fun exercise to figure out our column math for another video. So how do we choose lumber size, an adequate lumber size, to get ourselves to that image on the right? Well, it starts with the deflection criteria. And so let's take a look at this piece by piece. We see the triangle, the delta symbol. Delta allowable is less than or equal to L over 160, 240, and 360. I personally kind of stick with 240. 160 would be something like, okay, we want to see a bow happen on purpose. Like maybe it's funny or something. We want to see a bow happen on purpose, but make sure that it's safe. That L over 160 is how we get there. Like I said, I'll stick with L over 240, and then L over 360 would be used for a musical or dance, something that we just want to stay absolutely rigid under really dynamic loads, people jumping up and down, dancing, singing, all that kind of good stuff. And so let's take a look at our deflection case formulas. So we see up here uniformly distributed load. That's typically how I will do a deflection test, unless it's like a schedule 40, inch and a half schedule 40 pipe, where I need to run deflection on something hanging on a line set or an added pipe. So there you go. I almost never have to use the cantilever formulas. Alright, so working through the same problem that I had presented in the free body diagram earlier, except we're gonna shorten it down to 8 feet because that's kind of the length of our standard platform. So in the world of 4x8 platforms with a load of 100 pounds per linear foot, using the deflection criteria of L over 240, when we move forward, we're gonna first convert everything to inches. So we'll have our L in inches. 96 over 240 is how we will calculate our allowable deflection. And then 8.33 pounds per linear inch. This is actually a go-to test for me. I run with 100 pounds per linear foot in my standard deflection test because that is for a very specific reason. When we design 4x8 platforms, we're looking at a general load of 50 pounds per square foot, so 32 square feet of that. And if we divide it by 2 to see the load that each of our long sides of our platform is seeing, we can say, okay, 800 pounds divided by 8 feet, 8.33 pounds per linear inch. That's how we get there, and it's a perfect number to go to. So what I've done in the past is just make a spreadsheet with this formula in mind for each of our case formulas and run a multitude of tests for lumber, aluminum, and steel. And take a look at the bottom here. I've actually, if I step back, take a look at delta max equals 5 WL to the 4th over 384 EI. Let's break that down for a second. 5 times WL. WL is the load over the span to the 4th, divided by 384. That's an architectural ratio. I'm not going to think too much about that. And then E, the modulus of elasticity, times the moment of inertia. So this would be, we would use this if we already wanted to test a beam size in mind. Like, am I going to use a 2x4? Well, we would use the modulus and moment of inertia in this formula right here on this slide. But if we're just trying to figure out, hey, what size could I use? Well, we would want to use this version of the formula. We would want to test against the moment of inertia, and I'll show you why. In the back of this book, we have all these associated values with different lumbar sizes. So how do we get there? Well, let's step back. Running deflection over L over 240 in my calculator here, 96 over 240, which means that we can deflect about 0.4 inches, about 3/8 of an inch. We use that value in our formula below. You can see 5 times WL to the fourth, 8.33 times 96 to the fourth, divided by 384 times the modulus of pi, and then times that 0.4 from up above. And that spits out our figure, our moment of inertia required is 19.19923. There's really no reason to keep that many decimal places, but calculators are going to calculate. And so taking that information and looking at page 467 in the back of this book, we can start to cross-reference to say, hey, what is an adequate beam size for this 96-inch long platform, this 8-foot long platform? Well, it looks like it's a 2x6 because the IXX value, and if you look at this drawing to the right, you can see the X and the X are going across this cross section in the strong orientation of the 2x4. So 2x4 stands up straight, that's the strong orientation. If it's tilted 90 degrees, that's the weak orientation. And so we can see that the IXX value is 20.8, and we're comparing that to 19.1923, etc. Okay, so that's great. We know that a 2x6 is safe. Well, what if we wanted to work in lumber and say, well, what if we had a skinnier platform? What could we use there? Well, we may not want to stick with wood because in this particular instance, it's looking like we might want to use a 4x6 on its side, which is the same, it's the same depth as a 2x4, but that gives us an IYY value of 19.651, which, there's really no point in us using that. But it's a really good opportunity for us to start examining this formula, and instead of using lumber values for the modulus of elasticity, let's go ahead and try steel or aluminum. And so that's just a look at this case load, this case formula. The good news that I want to share with you today is that there are a couple of apps out there. I created one of them. If you're on iOS, it's still in beta. So if you're an iPhone, the app may or may not work perfectly for your model of iPhone. But if you're on Android, it seems to be working for everybody. But you basically just step through this app. You select your type of framing member. Theater Beams Light is only for wood design. So you'll get like a little flag if you try to select steel or aluminum. But you basically, you select your material, you input the number of inches, and then it provides you with a list of materials that you could use. It'll go down, can you use a 1x8 or a 2x4, etc. It'll let you know after you input the number of inches. So it's a very good tool to use, and the fact that it's on your phone, you keep it in your pocket. If you're trying to just build something on the fly without drawing in a computer, or you're just doing a really quick rough sketch, hey, 120 inches, what size beam do I need? Well, give Theater Beams Light a try. It's completely free, and I really hope that the whole point of this app and why I made it is to just make this kind of problem solving accessible, because there's a lot of TDs out there that want this knowledge, and rather than second guessing themselves or potentially overbuilding or accidentally underbuilding, here's a resource that can help you make these choices. So anyway, that was deflection criteria in 20 minutes, which was super fast. But please, you can reach out to me via the Theater Squared website, or my name is Alex Worthington. Reach out to me on any social media platform if you have any questions. I'm happy to step through any of these processes a little bit longer and more thorough. But today is really just about, giving people that don't have this mathematical experience just a little bit of a look into how technical designers and engineers alike run deflection, and why they run deflection before we even worry about failure modes. So that's my presentation on deflection. I hope you enjoyed it. I hope you found it informative. Thank you.